Welcome, my name is Cristina Losada, and I am an associate professor at the University of Alcalá, in Spain. I'm going to present this session that is focused on data acquisition. This MOOC has been developed in the context of the Erasmus Plus project, Grateful Equalizing of Mechatronics Students, or GEMS. The schedule of this session includes 5 sections. First, we will introduce the concept of data acquisition and explain why it's necessary in a mechatronic system. After that, we will define the main characteristics of analog and digital signals. The next sections will be related to the analog to digital conversion. Finally, we will see the main conclusions and the bibliographic references. So, let's start with the introduction. Normally, when we measure a physical magnitude, such as sound, temperature, light, etc. with a sensor, we get an analog signal. However, the processing is usually done with a digital device, that could be an Arduino or an STM32. Therefore, we need to convert these analog signals into digital ones for further processing. Then, data acquisition can be defined as sampling signals that measure a physical phenomena and converting them into a digital form for being processed in a digital device. This process can involve several steps and different elements, as shown in the diagram. The first element is the sensor or transducer that converts the physical magnitude into an electrical analog signal. In this example, the sensor is a microphone that measures sound pressure. It may then be necessary to condition this electrical signal to improve its characteristics. For example, in the case of the microphone, we can use an amplifier or even a filter to reduce the noise. After that, the analog signal can be converted into a digital one using an analog to digital converter, or ADC. From this diagram, both transducer and signal conditioning has been addressed in the previous modules of this MOOC. Since this module is focused on data acquisition, in the following section we will go deeper into the characteristics of analog and digital signals, as well as the analog to digital conversion. It's time to speak about analog and digital signals. As we have just seen, in a typical sensory system coexist analog signals with digital ones, since the sensors provide analog measures, whereas the processing is carried out in a digital device. So, there are required an ADC. Analog signals represent continuous data using a continuous range of values, so they can take any value at any time, as could be the height of a balloon. On the other hand, digital signals can only take values within a finite set and at a given time, as could be the step on a staircase that only can have discrete values, 1, 2, 3, etc. I'm sure that you can find other examples of digital and analog devices. If we analyze the main characteristics, analog signals are more accurate, as they can take any value at any time. However, due to this, analog signals are also more sensitive to noise, because a small modification in the value causes the signal to change. Regarding digital signals, they are less sensitive to the noise, because only large values of noise can change the signal value. Furthermore, the signals can be processed using digital devices. However, since the number of possible values is limited, digital signals are less accurate than analog ones, and there can appear errors due to quantization. Now that we have seen the main characteristics of analog and digital signals, let's move on to analog to digital conversion, starting with the definition and then explaining the 2 main steps, sampling and quantization. An ADC converts an analog voltage to a digital value representing its magnitude. Thus, the input of an ADC is the analog signal, and the output is a digital signal, that is, a digital code with n bits to represent the input values. So, the starting point is the analog signal. The conversion is then performed in 2 steps. First, the analog signal is sampled, taking its values periodically at some points in time. Specifically, it's sample time. At this point, we have a sample signal whose values can only change at certain points in time, but they can still have any value. Since a digital signal can only take values within a finite set, the second step is quantization. It consists of replacing each real number with an approximation from a finite set of discrete values. It's important to note that the number of available values depends on the resolution, that is, the number of bits that we use to represent the digital code at the output of the IDC. As we have just seen, the sampling consists of measuring the amplitude of the analog signal at discrete time instants to obtain a sample signal. The ideal sample can be represented as a switch that is periodically closed, obtaining at these times the value of the input signal. In this process, the time between two consecutive measurements is called the sample time, and its inverse is the sampling frequency, that is defined as the number of measurements per second. These are very important parameters directly related to the quality of the digital signal, and they must be chosen very carefully. So, if we have an analog signal, how do we choose the sampling frequency? First, it's important to note that the higher the sampling frequency, the more similar the sample signal will be to the continuous one, thus reducing the conversion error. However, it also produces an increment in the computational cost, so it's important to get a balance between these two aspects. On the other hand, reducing the sampling frequency reduces the computational cost, but it increases the conversion error. And if the frequency is too small, it may be impossible to reconstruct the continuous signal from the sample one. Regarding that, the Nyquist sampling theorem provides a lower limit for the sampling frequency. This theorem states that the sampling frequency must be at least twice the highest frequency of the continuous signal to be able to reconstruct the original signal. Let's see an example with the signal in the picture. We can sample this signal with a sampling frequency that is exactly twice the signal frequency. It means that we get two samples for each signal period. So, with this information, we can reconstruct the analog signal from its samples. But we can reduce the sampling frequency, for example, making it 1.5 times the signal frequency, as in the sample at left. In this case, we can see that we do not have enough information about the original signal from its samples. It's important to note that the Nyquist theorem provides a lower limit for the sampling frequency, but in some cases, we need to have more information about the analog signal, so we can increase the sampling frequency. For example, taking 10 samples per period, as shown in the sample at right. After sampling, the last step in the analog to digital conversion is the quantization, so that the amplitude values of the sample signal are approximated to those in a finite set of possible values. At this step, the most important parameter is the resolution, given by the number of bits that are available to represent the digital code. So, if we have n bits, the number of possible values is 2 to the power of n. In the table, we have the number of available levels for different values of n. For example, if we have 8 bits, the number of levels will be 256, from 0 to 255. Whereas for 12 bits, the number of levels increases until 4096, what is 16 times greater. But even though the number of bits increase, there is always a quantization error because we only have a finite set of possible values to represent a signal that can take infinite continuous values. Knowing the resolution, we can determine the maximum quantization error, which is defined as the ratio between the maximum input value and the number of levels. So, as we increase the number of bits, the number of levels also increase, and the quantization error decrease. However, it increases the computational cost and the hardware resource required in the converter. The quantization assigns a digital code to each input voltage value. Specifically, the ADC assigns the minimum value 0 to 0 volts and the maximum one, 2 to the power of n minus 1, to the power supply voltage. Thus, the ratio between the ADC output code and its input voltage is given by the equation shown, from which we can clear the output digital code as a function of the input analog value. To finish this section, let's see how quantization works with a numerical example. We want to obtain the output code if the input voltage is 2.18 volts, the power supply is 5 volts, and the ADC has 10 bits. Moreover, we also want to compute the maximum quantization error. At this point, you can pause this video and try to compute the required values. If we replace the given values at the previous equation, the result is 446.028. But we can't represent floating point values with our digital code, so we need to round the results, obtaining that the code is 446. Regarding the maximum quantization error, is the ratio between the power supply voltage and the number of levels, so in this case, we obtain a maximum error close to 5 millivolts. Note that we have already seen the two steps required to convert an analog signal into a digital code. The next section is focused on the ADC working principle. This diagram shows the general idea of how an ADC works. It compares the sampled analog signal with another analog signal obtained from a digital code. In the following slides, we will take a closer look at each of the elements shown in this diagram. The first element is the sample and hold, which is responsible for sampling the input signal. To do this, the sample and hold measure the input value periodically, every sample time, and holds the measured value at its output until the next sample time. Thus, the output of this module is a sample signal. Another important module in the ADC is the one that generates the digital codes, that will then be converted to an analog signal for comparison. The way these codes are generated determines the maximum conversion time. The first approach is named the staircase ramp, and it's based on a counter that increases its output iteratively. This is a simple solution, but if we start at 0 and the input voltage is close to the maximum, it can take a long time for the counter to reach the correct value. To reduce this time, a widely used solution is based on a successive approximation register, named SAR, which is the one used in the ADCs in the ESP32, in the GEMS prototype. We will analyze this solution in detail later. Before comparing the digital code to the sample input, it's necessary to convert it to an analog signal. This is done by using a digital to analog converter, or DAC. All the elements included in this structure allow generating digital codes and comparing the corresponding analog signal to the sample input signal until the difference between them is lower than the maximum conversion error, what means that the compared code is the corresponding to the input signal value. Returning to the SAR ADC, the one in the ESP32, it generates the digital codes iteratively using an algorithm based on the binary search. Thus, the first value is chosen in the middle of the set of possible values. For example, if we have 3 bits, the values will go from 0 to 7, and we start at 4. Then, if the input voltage is greater than the voltage obtained from the selected code, the new value is obtained in the center of the upper half. And if the input voltage is lower, the new value is obtained in the center of the lower half. This process is repeated iteratively until the code corresponding to the input voltage is reached. We can see how it works with an example. Here we have a 4-bit ADC, and we want to obtain the output digital code if the analog input is 3 volts and the supply voltage is 4.5 volts. Since the number of bits is 4, we have 16 possible codes from 0 to 15. First, we obtain the resolution, that is 0.3 volts for each code. That is, the code 1 corresponds to 0.3 volts, the code 2 corresponds to 0.6 volts, and so on. And we start with the central code, that is the 8. In binary, it is 1, 0, 0, 0. If we convert this code into an analog signal, we obtain a signal of 2.4 volts, that is then compared with the input sample signal. Since 2.4 is lower than the input signal, we search only in the upper half. At this point, we already know that the first bit in the code is 1. The next code is the one in the middle of the upper half, 1, 1, 0, 0. That provides an analog voltage of 3.6 volts, higher than the input voltage. Then the second bit is a 0, and the next code will be 1, 0, 1, 0. If we repeat the process with the code 1, 0, 1, 0, we obtain a voltage of 3.0 volts. That is equal to the input 1. So we have finished the conversion, being the output code 1, 0, 1, 0, or 10 in decimal. We are almost finished this lecture. It's time for some conclusions and references. Summing up the session, we review now the main ideas about data acquisition. In a typical sensory system, the sensors provide analog signals while the processing is done in a digital device. So, analog and digital signal coexist. Therefore, converters are needed. In this context, analog to digital converters convert an analog voltage to a digital code representing its magnitude. This process is carried out in 2 steps, sampling and quantization. And it's very important to take into account that the sampling frequency must satisfy at least the Nyquist theorem, and the number of bits determines the precision of the conversion. There exist different types of ADC depending on how the digital codes are generated. The ESP32, the one in the GEMS prototype, integrates two 12-bit SAR ADCs that can be used to obtain data from different sensors. This last slide includes the recommended references, some of them used in this lecture. References from 1 to 3 are directly related to data acquisition and analog to digital conversion, whereas the last 3 references are focused on the specific ESP32 ADC characteristics. And that's all. Thanks for watching.